Now my topic is a current loop behave like a magnetic dipole of moment I into a. That means when a current is circulating in orbit or circulating in a coil, that circulating current behave like a magnetic dipole, and the dipole has a moment I into a current into area of that loop. Okay, to prove this, suppose we have already derived from Biot-Savart law. Suppose this is our coil or loop of current. Okay, this is a loop of current, circular loop of current. Current is flowing in this direction. Suppose I, and the radius of that loop is say A. Okay, now from the axis we have a point P which is at a distance r from the center of the coil or loop. Okay, so by Biot-Savart law we have magnetic field at that point. B is nothing but mu 0 I square divided by 2 into a square plus r square whole to the power 3 by 2. Okay, this is our expression. Now consider A is very less than r, then that means that point P is far away from your loop. So a square plus r square is nearly equal to r square. So your B now becomes mu 0 I square 2 into a square plus r square means now r square to the power 3 by 2, and your expression now becomes mu 0 I square divided by 2 r cube. Mu 0 by 4 pi, one can write this as mu 0 by 4 pi into, now it is 2I into pi square by r cube. Okay, so just 2 to cancel, you got t 2 by here, and if you cancel 4 pi, so just multiply numerator and denominator by 2 pi. Okay, in numerator additional 2 pi comes term additional 2 pi term come, so in numerator we multiplied by 2 pi, so also in denominator we multiplied by 2 pi, so then this 2 converted into 4 pi. So your expression now becomes mu 0 by 4 pi into 2I. What is pi square? Pi square is the area of that coil or loop. Pi square is the area of that loop. Okay, so I into A by r cube. Okay, and we have our magnetic field is directed away from the center for this direction of the current. Okay, that means if an observer is sitting over here and he look to the coil, he observed that the coil is actually rotating in the anti-clockwise direction. Okay, anti-clockwise direction. So this is for anti-clockwise current, your magnetic field is outward, and that is given by mu 0 by 4 pi 2IA by r cube. And you have already derived in my last video that if it is a magnetic bar magnet of magnetic moment M, then a magnetic field at a distance r from the center is mu 0 by 4 pi 2m by r cube. Okay, this is our magnetic field at this point, and it is outward also when this n pole facing to the point P. Okay, this is magnetic field. So comparing this equation 1 and that equation we have derived earlier, we just have this M is nothing but I into A. Okay, So magnetic dipole moment of a closed loop carrying current I is current into area. Okay, current into area, and hence it is proved. But some more concept has to be developed over here, that as we have discussed for bar magnet, this side is N, this side is S, that's why your magnetic field is outward. Similar here, it is anti-clockwise current, so magnetic field is outward. Okay, so anti-clockwise current is equivalent to magnetic north pole. Why so? Suppose this is anti-clockwise current, so we can draw N over here. Okay, so this anti-clockwise current is equivalent to north pole. So as this observer observed towards this side, so this is north pole, so from this side this would be your south pole. Okay, so your lines of force actually outward, okay, outward from the north pole, so inward to the south pole. So suppose if you draw clearly over here, this is your coil carrying current. So if you draw from the upside, this is your anti-clockwise, that means this is your anti-clockwise, that means this is your north pole. So your lines of force coming from here. Okay, then downside would be your south pole, and then your lines of force entering into the south pole. Okay, if reverse thing happened here, that means the current is in this direction, that means if you observe from the upward, your current is opposite, that means it is in the clockwise direction now, so it would be now your south pole. Then lower side would be north pole, that means lines of force enter at the lower side and coming lines of force would be lines of force, because this side is N, so lines of force is coming out from the lower end and enter into the upper end. Okay, so so current loop behave like a magnetic dipole. One face is equivalent to north pole, other face is equivalent to south pole, and its magnetic dipole moment is nothing but I into A. Okay, so when your current is anti-clockwise, again when your current is anti-clockwise, that means your magnetic dipole moment is upward, and when your current is clockwise, then your magnetic dipole moment vector is downward. Okay, this is one more understanding, because always because when anti-clockwise, this side is north pole, so magnetic pole, and this side is south pole, so magnetic dipole moment is from south to north, and it is clockwise, upside is south pole and downside is north pole, and magnetic dipole moment is from south to north. That's why anti-clockwise gives magnetic dipole moment upward, and clockwise current gives magnetic dipole moment downward. That's why anti-clockwise current gives magnetic moment vector upward, and clockwise current gives magnetic dipole moment downward. Okay, you have to understand these things. Okay, next I do some more calculations on magnetic dipole. Okay, do some more calculations on magnetic dipole on my next video.